Right now, as you listen to these words, you exist in 3 dimensions of space. You can move forward and backward. You can move left and right. You can move up and down. These 3 directions, these 3 dimensions, form the entirety of the space you can physically navigate. Every object you've ever touched, every place you've ever traveled, every star you've ever seen exists within this 3-dimensional reality. It's so fundamental to your experience that you rarely stop to question it. But beneath the surface of this comfortable, observable reality lies one of the most profound mysteries in theoretical physics. According to our most promising theories of how the universe operates at its deepest levels, these 3 spatial dimensions that feel so complete, so total, represent only a fraction of the dimensional structure of space itself. String theory, our leading candidate for a unified theory of everything, suggests that space actually possesses 9 spatial dimensions, not 3. And when you include time, the universe operates in 10 dimensions. M theory, an even more encompassing framework, requires 11 dimensions total. 10 spatial dimensions plus time. This isn't science fiction, this is serious physics, developed by thousands of the world's most brilliant minds over decades of careful mathematical work. These extra dimensions aren't optional decorations added to make the theories more interesting. They're requirements. Without them, the mathematics breaks down. The theories become inconsistent. The equations refuse to describe a stable, sensible universe. So where are these hidden dimensions? Why can't you see them, feel them, or move through them? Why does the universe you experience contain only 3 dimensions of space when the fundamental fabric of reality apparently requires 6 or 7 more? And, perhaps most intriguingly, why did the universe settle on 3 large spatial dimensions in the first place? Was it inevitable, or could things have turned out differently? For the next 2 hours, we're going to explore these questions together. We'll journey through more than a century of physics, from the early 20th century dreams of unifying all forces, through geometry, through the string theory revolution of the 1980s, to the cutting-edge ideas being tested at the Large Hadron Collider today. We'll discover that the answers involve some of the most beautiful mathematics ever conceived, connect to the deepest mysteries about the nature of space and time, and reveal that reality may be far stranger and more intricate than anything we directly perceive. The pace will be gentle. The explanations will be thorough. And while the subject matter ventures into realms beyond everyday experience, every concept will be grounded in verified physics and presented in language designed for understanding, not bewilderment. Let's begin by truly understanding what we mean when we talk about dimensions and why the 3 we experience are so special. When physicists talk about dimensions, they mean something specific and mathematical, but the concept maps beautifully onto your everyday experience. A dimension is simply an independent direction in which you can move. Independent means that moving in one dimension doesn't require moving in any other. Think about standing in an empty room. You can walk forward toward the wall in front of you or backward toward the wall behind you. That's one dimension. Let's call it the forward-backward dimension. You can also sidestep left or right, moving along a wall. That's a second dimension, completely independent of the first. You moved without going forward or backward at all. Finally, you can jump up or crouch down. That's the third dimension, the up-down dimension. These 3 dimensions are mutually independent. You can combine them, walking forward while moving right while jumping up, but each represents a distinct direction of possible movement. Now here's the crucial insight. Any movement you can make, no matter how complex, can be broken down into combinations of these three fundamental directions. If you walk diagonally across the room, you're simultaneously moving forward and left. If you climb stairs, you're moving forward and up at the same time. The universe never requires you to move in a fourth spatial direction that's somehow perpendicular to all three of these. 3 dimensions are sufficient to describe every possible location and every possible motion. Mathematicians express this by saying that 3-dimensional space has 3 degrees of freedom. To specify any location in your room, you need exactly 3 numbers: how far from one wall, how far from another wall, and how far from the floor. In a coordinate system, these are typically called X, Y, and Z. 2 numbers wouldn't be enough. They'd only pinpoint your location on a flat surface, like a map. 4 numbers would be redundant. 3 always suffice. This 3-dimensional structure of space isn't arbitrary. It has profound consequences for physics. For instance, the force of gravity follows an inverse square law. Double your distance from a massive object, and you feel 1/4 the gravitational pull. This inverse square relationship arises directly from 3-dimensional geometry. Gravity spreads out in all 3 dimensions, so its influence dilutes according to the surface area of a sphere, which grows with the square of the radius. In a universe with different numbers of spatial dimensions, gravity would follow different mathematical rules. 3 dimensions also determine the kinds of stable structures that can exist. In our 3-dimensional universe, planets can orbit stars in stable elliptical paths that last for billions of years. The mathematics of orbital mechanics work out beautifully in 3 dimensions, but physicists have calculated that in a universe with 4 or more large spatial dimensions, stable, planetary orbits would be impossible. Planets would either spiral into their stars or fly off into space. Similarly, atoms would behave differently. The inverse square law that keeps electrons bound to atomic nuclei depends on 3-dimensional geometry. In 4 spatial dimensions, atoms might not form stable structures at all. So our 3-dimensional experience isn't merely how we happen to perceive space. It's a fundamental property of the physical world that shapes everything from the force of gravity to the possibility of complex chemistry, from the orbits of planets to the structure of atoms. It's woven into the fabric of reality as deeply as any property could be. Yet, when physicists push deeper into understanding the fundamental forces and particles, when they tried to build theories that could unify gravity with quantum mechanics, that could explain why particles have the masses and charges they do, that could describe the universe at the smallest possible scales, they kept encountering the same surprising requirement. The mathematics only worked in higher dimensions. 3 spatial dimensions weren't enough. The theories needed more room to operate, more geometric structure to contain all the necessary physics. This presents an extraordinary puzzle. On the one hand, we have overwhelming experimental evidence that space has 3 dimensions. We can measure distances, track particles, map the universe, and everything behaves exactly as 3-dimensional geometry predicts. On the other hand, we have compelling theoretical reasons to believe that space must have more dimensions than 3. Our best theories of fundamental physics seem to require it. The resolution of this puzzle, the way physicists reconcile these apparently contradictory facts, involves one of the most elegant and surprising ideas in all of theoretical physics. But to understand it, we need to trace the history of how physicists first realized that extra dimensions might exist. That story begins in 1919, just 4 years after Einstein published his general theory of relativity, when a little-known German mathematician made a stunning discovery. In November 1919, a mathematician named Theodor Kaluza, working at the University of Königsberg, sent Albert Einstein a remarkable paper. Kaluza had been thinking about Einstein's recently published general theory of relativity, which described gravity as the curvature of four-dimensional spacetime. What if, Kaluza wondered, spacetime wasn't four-dimensional, but five-dimensional? What would Einstein's equations look like in 5 dimensions instead of 4? When Kaluza performed this mathematical exercise, simply taking Einstein's gravitational field equations and rewriting them in 5 dimensions instead of 4, something astonishing happened. The equations naturally split into 2 distinct parts. One part looked exactly like Einstein's original equations describing 4-dimensional gravity, but the other part looked like Maxwell's equations for electromagnetism. Electromagnetism and gravity, which seemed like completely separate forces with different characteristics and different mathematical descriptions, appeared to be unified in 5-dimensional geometry. The electromagnetic field emerged automatically from the 5-dimensional gravitational field. Electric charge corresponded to motion in the 5th dimension. A positively charged particle was moving one way through the 5th dimension, while a negatively charged particle moved the other way. Einstein was initially cautious about Kaluza's idea, but he eventually recommended the paper for publication in 1921. The concept was beautiful, too beautiful to dismiss. For the first time, someone had shown how 2 of nature's fundamental forces might be different aspects of a single geometric structure, if only space had 1 extra dimension beyond the 3 we observe. But this raised an obvious question. If there's a 5th dimension of space, why don't we see it? Why can we only move in 3 spatial directions? In 1926, the Swedish physicist Oskar Klein provided an answer by incorporating quantum mechanics, which had just been formulated in its modern form. Klein proposed that the 5th dimension wasn't absent, it was compactified. It existed at every point in our familiar 3-dimensional space, but it was curled up into a tiny circle so small that we couldn't perceive it or travel through it. To understand Klein's idea, imagine a garden hose lying across a lawn. From far away, the hose looks like a 1-dimensional line. You can only perceive motion along its length. But an ant walking on the hose's surface would discover 2 dimensions. The long dimension stretching the length of the hose, and a circular dimension wrapping around its circumference. The circular dimension is always there, but it's only apparent at small scales. Klein calculated that if the 5th dimension was curled up into a circle with a radius around 10 to the negative 33 centimeters, far, far smaller than an atomic nucleus, it would be completely undetectable by any technology of his time. The dimension would exist at every point in space, but it would be so tiny that particles moving through it would appear to us as particles with different electric charges sitting still in our 3-dimensional world. This Kaluza-Klein theory, as it came to be called, was extraordinarily elegant. It showed that extra dimensions were possible, that they could be hidden through compactification, and that their existence could have observable consequences even if we couldn't directly perceive them. However, the theory had limitations. It couldn't explain the weak and strong nuclear forces, which weren't discovered until later. It made some predictions that didn't match experimental observations, particularly regarding the masses of particles. And it didn't fully incorporate quantum mechanics in a consistent way. As physics advanced through the mid-20th century, Kaluza-Klein theory faded somewhat into the background. Physicists developed the standard model of particle physics, which successfully described electromagnetism, the weak nuclear force, and the strong nuclear force using quantum field theory without requiring extra dimensions. Gravity remained separate, described by Einstein's general relativity in four-dimensional spacetime. The dream of geometric unification seemed to have reached a dead end, but the seed had been planted. Kaluza and Klein had demonstrated that extra dimensions were mathematically possible, that they could be hidden from view, and that geometry could encode information about forces and charges. These insights would prove crucial decades later when physicists discovered that a completely different approach to understanding fundamental physics, string theory, also required extra dimensions. And this time, the number of dimensions needed was even larger. String theory emerged in the late 1960s from attempts to understand the strong nuclear force, the force that holds atomic nuclei together. Physicists noticed that certain mathematical patterns in particle interactions resembled the vibrations of a one-dimensional string. Initially, this string theory was thought to describe only the strong force, but by the mid-1970s it became clear that the theory actually described something far more fundamental and far stranger. The core idea of string theory is radical. Instead of treating particles as infinitesimal points with no internal structure, string theory proposes that the fundamental constituents of matter are tiny, vibrating strings of energy. These strings are unimaginably small, around 10 to the negative 33 centimeters in length, the Planck length, named after Max Planck, which represents the scale where quantum effects of gravity become important. Each different particle we observe, electrons, quarks, photons, gluons, represents a different vibrational pattern of these fundamental strings, just as different musical notes correspond to different vibrational modes of a violin string. An electron is a string vibrating in one pattern. A quark is a string vibrating in a different pattern. The masses and charges of particles are determined by how the string vibrates. Strings can be closed, forming loops, or open with two endpoints. They move through space, tracing out two-dimensional surfaces called world sheets. When strings interact, when an electron scatters off a photon, for instance, their world sheets connect and split in specific mathematical ways. What makes string theory particularly compelling is that it naturally includes gravity. One of the vibrational patterns of a closed string has exactly the properties required for the graviton, the hypothetical quantum particle that carries the gravitational force. This means string theory is, by its very construction, a quantum theory of gravity, something that had eluded physicists for decades. General relativity and quantum mechanics, which seem incompatible when you try to combine them using conventional methods, merge naturally in string theory. But there's a catch, a profound, unavoidable catch that leads directly to our discussion of extra dimensions. When physicists wrote down the mathematical equations governing how strings vibrate and interact, they found that these equations were only consistent, only mathematically sensible, in specific numbers of dimensions. For the equations to avoid infinities and contradictions, for the theory to describe a universe that made sense, space-time couldn't have just 4 dimensions. It needed to have exactly 10 dimensions. 9 dimensions of space plus 1 dimension of time equals 10-dimensional space-time. This wasn't a choice. It wasn't an adjustable parameter. The number 10 emerged directly from the mathematics. In any other number of dimensions, the theory produced nonsensical results. Infinite probabilities, negative probabilities, violations of quantum mechanics. Only in 10 dimensions did everything work correctly. Why 10 specifically? The answer lies in quantum mechanics and the requirements of mathematical consistency. When a string vibrates, those vibrations must satisfy quantum mechanical constraints. In quantum mechanics, certain quantities must be conserved, certain symmetries must be respected, and certain mathematical operations must give finite, sensible answers. These requirements translate into specific conditions on the dimensionality of spacetime. For the technically inclined, the requirement comes from something called conformal invariance on the string worldsheet. The physics of a string must look the same regardless of how you stretch or compress the worldsheet coordinates. This conformal symmetry is crucial for the theory's consistency. But maintaining this symmetry requires cancelling what's called the conformal anomaly, and that cancellation only occurs when the total number of spacetime dimensions equals 10 for superstrings or 26 for the earlier bosonic string theory. Superstrings, which include fermions, the particles that make up matter, require 10 dimensions. By the mid-1980s, physicists had discovered not just one string theory, but 5 distinct versions, each consistent in 10 dimensions. These were called Type 1, Type 2A, Type UIB, SO32 heterotic, and E8X-E8 heterotic string theory. The theories differed in details, whether they included only closed strings or also open strings, how left-moving and right-moving vibrations on the string were treated, what kinds of symmetries they possessed. All 5 theories successfully unified gravity with the other forces. All 5 were mathematically consistent. All 5 required exactly 10 dimensions. And all 5 faced the same question that had confronted Kaluza-Klein theory decades earlier. Where are the extra 6 spatial dimensions? Why do we only observe 3? The answer, again, was compactification. Just as Klein had proposed that the 5th dimension curls up into a tiny circle, string theorists proposed that 6 of the 9 spatial dimensions curl up into elaborate geometric shapes at every point in our familiar 3-dimensional space. These compactified dimensions would be far too small to observe directly, but their geometric properties would determine the physics we observe in our 3-dimensional world. The shape of the compactified dimensions matters enormously. Different geometric shapes produce different low-energy physics. The masses of particles, the strengths of forces, even the number of particle families, all these observable properties depend on the specific geometry of the hidden dimensions. This means string theory doesn't make unique predictions until you specify the compactification geometry. And there are many, many possible geometries to choose from. For a time in the 1980s, it seemed like physics had 5 different consistent theories of everything, each requiring 6 hidden dimensions with no clear way to choose among them or determine the correct compactification geometry. The situation was simultaneously exciting. We had quantum theories of gravity, and frustrating, we had too many options, with no experimental way to distinguish them. Then, in 1995, a theoretical physicist named Edward Witten gave a talk at a string theory conference that changed everything. At the annual String Theory Conference at the University of Southern California in March 1995, Edward Witten presented a stunning proposal. The 5 different string theories, he argued, weren't actually different theories at all. They were 5 different ways of looking at the same underlying theory. They were 5 different limits, 5 different approximations of a deeper, more fundamental theory that existed in 11 dimensions, not 10. Witten called this hypothetical theory M theory. The letter M was deliberately ambiguous. It could stand for membrane or matrix or mother of all theories or mystery, since M theory itself remained poorly understood. But its consequences were immediate and dramatic. To understand what Witten discovered, we need to introduce a crucial concept that had emerged in string theory: duality. In physics, a duality is a relationship between two apparently different theories that actually describe the same physics. They're like two different maps of the same territory using different coordinate systems or projections. Physicists had discovered several dualities connecting the 5 string theories. For instance, type 2ia string theory at strong coupling, where strings interact strongly with each other, turned out to be equivalent to type 2ib string theory at weak coupling, where strings interact weakly. Similarly, the two heterotic string theories were related by a duality that exchanged certain properties. What Witten showed was that all these dualities fit together into a unified picture. The 5 10-dimensional string theories were all limiting cases of a single 11-dimensional theory. Just as a 3-dimensional object casts different 2-dimensional shadows depending on the angle of illumination, the 11-dimensional M theory cast 5 different 10-dimensional shadows depending on which limit you examined. But why 11 dimensions specifically? Where did that extra dimension come from? The answer connected to an older theory: 11-dimensional supergravity. Supergravity is a theory that combines supersymmetry, a theoretical symmetry between particles of different types, with general relativity. Physicists had proven in the 1970s that 11 dimensions was the maximum number in which you could construct a consistent supergravity theory. In 12 or more dimensions, the mathematics broke down. This 11-dimensional supergravity had been known for years, but it was thought to be just a toy model, not a fundamental theory of nature. Witten's insight was that this 11-dimensional supergravity was actually the low energy limit of M theory. Just as Newtonian gravity is a low energy approximation of general relativity, 11-dimensional supergravity approximates M theory when energies are low and quantum effects are small. The 10-dimensional string theories emerged when you compactified one dimension of M theory in different ways. If you curled up one dimension of M theory into a circle, you got type 2ia string theory. If you compactified it on an interval, a line segment with 2 endpoints, you got certain other string theories. The 5 string theories weren't fundamental. They were effective descriptions that emerged from M theory under different circumstances. But M theory brought another profound change. The fundamental objects were no longer just one-dimensional strings. M theory included extended objects of various dimensions called branes, short for membranes. A 0 brane is a point particle. A 1 brane is a string. A 2 brane is like a membrane. 3 branes, 4 branes, and higher dimensional branes also exist in the theory. In M theory, strings are just 1 branes. They're important, but they're not the only players. 2 branes, actual membranes, also exist and are equally fundamental. In 11-dimensional M theory, there's a 2 brane and a 5 brane. When you compactify to 10 dimensions, these branes can wrap around the compactified dimensions in various ways, producing all the different types of strings and branes observed in the 10-dimensional theories. The 11th dimension changed the entire conceptual framework. Before M theory, physicists thought about strings moving through 10-dimensional spacetime with 6 dimensions compactified. After M theory, the picture became more complex and more interesting. The universe might be 11-dimensional, with 7 dimensions, compactified. Or perhaps our entire 3-dimensional universe exists on a 3 brane embedded in higher dimensional space, a possibility called the brane world scenario. In brane world scenarios, the particles and forces we observe are confined to our three-brain. They can't escape into the higher dimensional bulk space surrounding the brain. But gravity is different. Gravity, corresponding to ripples in the fabric of space-time itself, can propagate through the bulk. This offers a potential explanation for why gravity is so much weaker than the other forces. Its strength is diluted because it spreads out in additional dimensions that the other forces can't access. The brain world picture is particularly relevant when we consider why extra dimensions might be larger than the Planck scale in certain models. In traditional string theory, the compactified dimensions were assumed to be Planck-sized, around 10 to the negative 33 centimeters. But in some brain world models, extra dimensions could be much larger, perhaps as large as a millimeter, without contradicting experiments, because only gravity would know about these dimensions. All our particle physics experiments probe the standard model forces, which would be confined to our brain. M-theory also resolved many puzzles about string theory. Mysterious dualities that seemed accidental turned out to be inevitable consequences of the underlying 11-dimensional structure. Mathematical tools that worked in one string theory, but not others, suddenly made sense as different aspects of the same 11-dimensional framework. The 5 apparently distinct theories formed a unified web of connections. However, M-theory brought its own mysteries. Despite 25 years of intensive work since Witten's 1995 proposal, we still don't have a complete formulation of M-theory itself. We understand many of its properties, particularly its low energy limit and its connections to the various string theories. We know it exists in 11 dimensions and includes extended objects of various dimensions. But we lack a fundamental description analogous to the string worldsheet formalism that works in 10 dimensions. This incompleteness doesn't invalidate M-theory or suggest it's wrong. Rather, it indicates we're still uncovering pieces of a vast theoretical structure. M-theory might be to its full formulation as general relativity was in 1915 compared to the geometric insights Einstein would develop over the following decade. For our purposes, the key takeaway is this. Our best current understanding suggests that fundamental physics requires 11 dimensions, 10 spatial, 1 temporal. 7 of those spatial dimensions are hidden from our direct perception through compactification. The geometry of these hidden dimensions, and potentially our confinement to a brain, determines everything we observe about particle physics and forces in our three-dimensional world. But this raises the question we've been circling. What does it actually mean for dimensions to be compactified? How can dimensions exist at every point in space but remain hidden? The answer requires understanding one of the most counterintuitive concepts in modern physics. The concept of compactification is central to understanding how extra dimensions can exist without being observable. At first glance, it might seem impossible. Either a dimension exists, and we should be able to move through it, or it doesn't. How can something be both present and hidden? The key is understanding that dimensions don't have to be large and extended like the 3 we experience. They can be compact, curled up into closed loops or complex geometrical shapes so small that moving through them is imperceptible. Let's start with the simplest example. A compactified dimension that's curled up into a circle. Imagine the entire universe has an extra dimension, but that dimension forms a tiny circle at every point in our familiar three-dimensional space. If you could somehow move in this circular dimension, you would return to your starting point after traveling a distance equal to the circle's circumference. This distance, the size of the circle, is called the compactification radius. Now imagine the circle's radius is extraordinarily small, say 10 to the negative 33 centimeters. That's the Planck length, roughly a billion times smaller than an atomic nucleus, which is itself 100,000 times smaller than an atom. At such scales, moving around the dimension is meaningless in any practical sense. You'd need energies comparable to the Planck energy, about 10 to the 19th Geiger electron volts, to probe distances that small. Those are energies that existed in the universe only in the first instant after the Big Bang. For all ordinary purposes, including every physics experiment ever conducted, this compactified circular dimension would be invisible. Particles might have momentum in this direction, corresponding to their electric charge in Kaluza-Klein theory, for instance, but the dimension itself would be undetectable. From our perspective, space would appear three-dimensional, but the compactified dimension has real physical consequences. It affects how particles behave, what masses they have, what forces they experience. In Kaluza-Klein theory, motion in the fifth dimension manifests as electric charge. In string theory, the way strings wrap around compactified dimensions determines which particles exist and what properties they possess. Now, one circular dimension is relatively simple. String theory requires 6 compactified dimensions. M theory requires 7. These can't all be simple circles. The geometry becomes far more complex. To understand why, consider what happens when you try to compactify multiple dimensions into circles. You can arrange them in various configurations. The simplest is a 6-dimensional torus. Imagine a 6-dimensional version of a donut surface. But there are many other possibilities, and they're not all equivalent. Different compactification geometries produce different 4-dimensional physics. This is where Calabi-Yau manifolds enter the story, but before discussing those specifically, let's understand what general constraints determine possible compactification geometries. First, the compactified space must be consistent with quantum mechanics. String propagation on this space must be mathematically well-defined without infinities or contradictions. Second, the compactified space must preserve enough symmetry to give reasonable low-energy physics. Too much symmetry and you get unrealistic predictions. Too little and the theory becomes chaotic. Third, the space must be small enough to avoid experimental detection. The exact size depends on the details, but typically it's assumed to be around the Planck scale or perhaps slightly larger. These constraints are stringent, but they still allow for many possibilities. Mathematicians have catalogued hundreds of thousands of possible compactification geometries, each potentially giving rise to different 4-dimensional physics. This landscape of possible string theory vacua, different possible ways the compact dimensions can be configured, is both a feature and a challenge. It means string theory is flexible enough to potentially describe our universe, but it also means the theory doesn't make unique predictions without additional input. The compactification of dimensions also relates to energy scales. In quantum mechanics, probing smaller distances requires higher energies. To see the Planck length, you need Planck energy. This connection is fundamental to why extra dimensions at the Planck scale remain hidden. Our most powerful particle accelerators, like the Large Hadron Collider, reach energies around 10 to the 4th giga-electron volts, 100 trillioning, times smaller than the Planck energy. We're nowhere close to probing Planck-scale physics directly. However, even if extra dimensions are Planck-sized, they can still have observable effects. These effects emerge indirectly through how the compactified geometry influences low-energy physics. The pattern of particle masses, the strengths of forces, subtle correlations in particle behavior, all these could potentially carry signatures of the hidden dimensions geometry. Some theoretical models propose that certain extra dimensions might be larger than the Planck scale, potentially as large as a micrometer or even a millimeter. These large extra dimension models modify the predictions significantly. If extra dimensions were that big, they would produce observable effects in precision gravity experiments, modify how gravity behaves at small scales, and potentially be detected at particle colliders through missing energy signatures when particles escape into the extra dimensions. The Large Hadron Collider has searched for such effects extensively. No evidence has been found, which means that if large extra dimensions exist, they must be smaller than the experimental limits, currently around 10 to the negative 18 meters, about 1,000th of the width of an atomic nucleus, for certain models. So compactification solves the puzzle of how extra dimensions can exist without being obvious. They're not absent, they're simply too small to access directly with current technology. They remain part of the fabric of space-time at every point, but curled up so tightly that their presence only manifests through their indirect effects on the particles and forces we can observe. The specific shape of these compactified dimensions determines what those effects are, and for string theory to produce physics resembling our universe, with the particles, forces, and properties we observe, the compactified dimensions must take very special forms. They must be Calabi-Yau, manifolds. In 1976, a mathematician named Eugenio Calabi posed a conjecture about complex manifolds, geometric spaces with particular mathematical properties. Calabi conjectured that a certain class of these manifolds, those with vanishing first Chern class, would always admit special geometric structures called Ricci-flat-Kähler metrics. In 1978, Xingtung Yau proved Calabi's conjecture, and these spaces became known as Calabi-Yau manifolds in their honor. At the time, this was pure mathematics, with no obvious connection to physics. But 7 years later, in 1985, 4 physicists, Philip Candelas, Gary Horowitz, Andrew Strominger, and Edward Witten, realized that Calabi-Yau manifolds were exactly what string theory needed for compactification. Why Calabi-Yau manifolds specifically? The answer relates to supersymmetry. String theory isn't just a theory of vibrating strings, it's a supersymmetric theory, meaning it includes a symmetry relating bosons, force carrying, particles like photons to fermions, matter particles like electrons. This supersymmetry is crucial for the theory's mathematical consistency and for avoiding certain unphysical results. When you compactify string theory's extra dimensions, you want to preserve at least some of this supersymmetry in the resulting four-dimensional theory. Too much supersymmetry would give unrealistic physics. Particles would come in perfectly mass-degenerate pairs, which isn't what we observe. But some residual supersymmetry is desirable because it helps control quantum corrections and might explain hierarchies between different energy scales in particle physics. It turns out that compactifying on a Calabi-Yau manifold preserves exactly 1/4 of the original supersymmetry. This is often called N1 supersymmetry in the four-dimensional theory, and it's exactly the amount many particle physicists find attractive for extensions of the standard model. The Calabi-Yau condition, those mathematical properties about vanishing first Chern class and Ricci flatness, translates directly into preserving this partial supersymmetry. But what do Calabi-Yau manifolds actually look like? This is where things become genuinely difficult to visualize, because we're talking about 6-dimensional geometric spaces with complex structure. Our brains can't visualize 6-dimensional objects any more than a two-dimensional being could visualize a sphere. Nevertheless, we can describe some properties. Calabi-Yau manifolds are compact. They have finite extent in all directions, like the surface of a sphere rather than an infinite plane. They're smooth, without sharp edges or singularities. They have complex structure, meaning they can be described using complex numbers rather than just real numbers. And they satisfy Einstein's equations in vacuum. Their geometry is flat, in the sense that Ricci curvature vanishes, even though they're certainly not flat in the ordinary sense. Most importantly for physics, Calabi-Yau manifolds have holes. Not holes in the ordinary three-dimensional sense, but topological features called cycles, closed paths or surfaces within the manifold that can't be continuously shrunk to a point. A simple two-dimensional example is a torus, which has two types of cycles, one going the short way around the tube and one going the long way through the donut hole. A six-dimensional Calabi-Yau manifold has many more cycles of various dimensions. These cycles are crucial because strings can wrap around them. A string can wind around a cycle multiple times, and each different winding number corresponds to a different vibrational state, hence a different particle. The number and types of cycles in a Calabi-Yau manifold determine how many particle families appear in the low-energy theory. In the standard model of particle physics, we observe three families of particles. Electrons, muons, and tau particles are three versions of the same, basic type of particle, differing only in mass. Similarly, there are three families of quarks. This family structure is mysterious from a four-dimensional perspective. Why three families? Why not 1 or 17? In string theory compactified on a Calabi-Yau manifold, the number of families is related to the manifold's topology, specifically to a number called the Euler characteristic. A Calabi-Yau manifold with Euler characteristic equal to -6 would produce three families in the low-energy theory, exactly what we observe. The shapes and sizes of the cycles also determine particle masses and force strengths. A string wrapping once around a cycle has a different energy than a string wrapping twice, and these energy differences manifest as mass differences between particles. The volumes of various cycles in the Calabi-Yau manifold relate to coupling constants, numbers that determine how strongly forces interact with matter. This means the detailed geometry of the compactified dimensions encodes essentially all the information about particle physics. The standard model, with its seemingly arbitrary parameters, particle masses, force strengths, mixing angles, might all derive from the geometry of a six-dimensional Calabi-Yau manifold too small to observe directly. Mathematicians have discovered that there are many Calabi-Yau manifolds. Early estimates suggested thousands. More recent work has found hundreds of thousands, and the true number might be even larger. Each different Calabi-Yau manifold produces different four-dimensional physics. This is the string theory landscape, a vast space of possible universes, each corresponding to a different compactification geometry. Which Calabi-Yau manifold describes our universe? String theory doesn't currently answer this question. The theory doesn't predict which compactification geometry should be realized. Some physicists view this as a shortcoming. Without that prediction, string theory can't make detailed testable predictions about particle physics. Others suggest that perhaps many different geometries are realized in different regions of a vast multiverse, and we find ourselves in a universe with the particular geometry compatible with our existence. This anthropic reasoning is controversial among physicists. Calabi-Yau manifolds also exhibit a beautiful property called mirror symmetry. For many Calabi-Yau manifolds, there exists a partner manifold, a mirror with the same physics but reversed geometric properties. What's called complex structure in one manifold corresponds to Kähler structure in its mirror, and vice versa. This mirror symmetry has deep implications for string theory and has also proven valuable in pure mathematics, allowing mathematicians to solve previously intractable problems in geometry. The study of Calabi-Yau manifolds connects string theory to some of the most sophisticated mathematics ever developed. Algebraic geometry, differential geometry, complex analysis, topology, all these fields contribute to understanding these spaces. Conversely, questions from string theory have inspired new mathematics. The interaction between physics and mathematics in studying Calabi-Yau compactifications has been extraordinarily fruitful for both disciplines. For our purposes, the key point is this. The extra dimensions in string theory can't have arbitrary shapes. They must be Calabi-Yau manifolds, or at least spaces with similar properties. The geometry of these hidden dimensions determines everything we observe about particle physics. They're not merely mathematical abstractions, but encode the very structure of physical law. Yet these manifolds exist at scales so small they seem impossible to probe experimentally. To understand why they must be so small, and what happens at the scale where they exist, we need to explore the Planck scale, the realm where quantum mechanics, gravity, and geometry merge into something genuinely strange. In 1899, before the development of either relativity or quantum mechanics, the physicist Max Planck proposed a system of natural units. By combining three fundamental constants, the speed of light, Newton's gravitational constant, and Planck's quantum of action, later called Planck's constant, he constructed units of length, time, mass, and energy that didn't depend on arbitrary human choices. The Planck length, approximately 1.6 times 10 to the negative 35 meters, emerged from this calculation. At the time, it was merely a mathematical curiosity, a natural unit that might prove useful for calculations. Over the next century, as physicists developed quantum mechanics and probed deeper into the nature of space and time, the Planck length revealed itself to be far more than a convenient unit. It represents a fundamental scale in nature, the scale where the quantum properties of space and time become important, where gravity and quantum mechanics must be fully unified, where our ordinary concepts of geometry and causality might break down. To grasp how small the Planck length is, consider that an atomic nucleus is about 10 to the negative 15 meters across. That's tiny. 100,000 nuclei lined up wouldn't span the width of a single atom. But the Planck length is 20 orders of magnitude smaller than a nucleus. If you scaled a nucleus up to the size of the observable universe, the Planck length would scale up to about the width of a single tree. At the Planck scale, quantum fluctuations in the geometry of spacetime become comparable to the size of spacetime itself. The smooth, continuous fabric of space, described by Einstein's general relativity, gives way to something chaotic and discontinuous, often called quantum foam. Distances smaller than the Planck length might not have meaning in any conventional sense. The very concept of a smooth spacetime metric breaks down. This breakdown occurs because of a fundamental tension between quantum mechanics and general relativity. In quantum mechanics, the Heisenberg uncertainty principle says that you can't simultaneously know a particle's position and momentum with arbitrary precision. The more precisely you measure position, the more uncertain the momentum becomes. In general relativity, energy and momentum curve spacetime. When you probe very small distances, trying to localize something very precisely, the uncertainty in momentum, and hence in energy, becomes enormous. At the Planck scale, this energy becomes so large that it creates gravitational effects comparable to the scale you're trying to measure. The space-time itself fluctuates quantum mechanically. This is why physicists believe that a quantum theory of gravity, a theory that properly unifies quantum mechanics with general relativity, must become important at the Planck scale. Above this scale, you can treat gravity classically using Einstein's equations and use quantum mechanics for particles moving in a fixed space-time. Below this scale, you need quantum gravity. String theory provides such a quantum theory of gravity. The fundamental strings have a characteristic length scale called the string length, and this is typically assumed to be close to the Planck length, though it could potentially be slightly larger. At distances larger than the string length, strings appear point-like, and physics looks like conventional particle physics. At distances comparable to the string length, the stringy nature becomes apparent, and the physics changes fundamentally. The compactified extra dimensions in string theory are assumed to have sizes around the string length, hence around the Planck length. This is natural for several reasons. First, the string length sets the fundamental scale in the theory. It's the distance where stringy effects become important. Second, making the compact dimensions this small ensures they remain hidden from all current experiments. Third, at these scales, the distinction between geometry and quantum fluctuations blurs in precisely the way string theory describes. But why should extra dimensions be curled up at the Planck scale specifically? Why not at some larger scale where we could observe them? One answer comes from the stability of the compactification. In string theory, the sizes and shapes of the compact dimensions are determined by fields called moduli. These moduli have potential energies, and the configuration we observe should correspond to a stable minimum of this potential. For many compactifications, including those on Calabi-Yau manifolds, the stable minimum occurs when the compact dimensions have Planck scale size. Another answer relates to the hierarchy problem in particle physics. The masses of ordinary particles, like electrons and quarks, are around 1 giga-electron-volt. The Planck mass, which sets the scale for quantum gravity, is about 10 to the 19th giga-electron-volts, a factor of 10 to the 19th larger. Why are these scales so different? If extra dimensions were large, this could potentially explain the hierarchy. But if they're Planck-sized, the hierarchy remains, requiring other explanations. Some models of large extra dimensions propose that certain dimensions could be much larger than the Planck length, potentially even approaching millimeter scales, to address the hierarchy problem. In these models, the fundamental gravity scale, the scale where quantum gravity becomes important, would be much lower than the apparent Planck scale we measure. Gravity would appear weak because it dilutes into the extra dimensions. These models make testable predictions, particularly for deviations in gravitational force at small distances, but so far, no such deviations have been observed. The Planck scale also marks the energy where the early universe was governed by quantum gravity. In the first 10 to the negative 43 seconds after the Big Bang, the Planck epoch, the universe was so hot and dense that quantum gravitational effects dominated. Our equations from general relativity and quantum field theory, which work beautifully at later times, break down during the Planck epoch. Understanding this earliest phase of cosmic history requires a quantum theory of gravity, like string theory or M theory. It's possible that during the Planck epoch, more than 3 dimensions were large. Perhaps the universe initially had higher dimensional symmetry, with all spatial dimensions on equal footing. As the universe expanded and cooled, 6 dimensions compactified while 3 remained large, leading to the universe we observe. The mechanism by which this dimensional compactification occurred is called moduli stabilization, and it's an active area of research in string theory and cosmology. The Planck scale represents more than just the size of extra dimensions. It's the fundamental scale of quantum gravity, the point where our current understanding reaches its limits, the energy regime where the deepest laws of physics manifest. Everything we observe, particle physics, chemistry, biology, astronomy, emerges from physics at the Planck scale, just as the properties of a material emerge from the behavior of its atoms. Understanding the Planck scale and what happens there is one of the grand challenges of theoretical physics. String theory and M-theory offer frameworks for describing Planck scale physics, but we lack experimental access to these energies. The Large Hadron Collider reaches about 10 to the 4th giga-electron volts, impressive by everyday standards, but still 15 orders of magnitude below the Planck energy. This experimental gap is profound. We can't directly probe the Planck scale or the compactified extra dimensions. We can't watch strings vibrate or observe the geometry of Calabi-Yau manifolds. All our evidence must come indirectly through how Planck scale physics influences lower energy phenomena that we can measure. So physicists search for these indirect signatures. They look for subtle effects, tiny deviations from known physics, patterns that might reveal the hidden dimensions. And they continue to refine the theories, pushing the mathematics further, hoping that theoretical insights will suggest new ways to test these ideas. Let's explore what experimental searches for extra dimensions have found so far. If extra dimensions exist, even if they're too small to observe directly, they should produce detectable effects in high-energy physics experiments. The challenge is identifying what those effects might be and designing experiments sensitive enough to find them. The most powerful tool for searching for extra dimensions is the Large Hadron Collider at CERN, near Geneva, Switzerland. The LHC is a circular particle accelerator 27 kilometers in circumference, built in a tunnel 100 meters underground. It accelerates protons to 99.90991% of the speed of light and smashes them together at energies up to 14 tera-electron volts, 14 trillion times the rest mass energy of an electron. When protons collide at these energies, their constituent quarks and gluons interact violently, converting energy into new particles. Detectors surrounding the collision points record these particles, and physicists analyze millions of collisions looking for patterns. Most collisions produce familiar particles: quarks, gluons, electrons, muons, W and Z bosons, and occasionally Higgs bosons. But occasionally, something unexpected might appear. Extra dimensions could reveal themselves in several ways at the LHC. One signature would be the production of Kaluza-Klein particles. Remember that in Kaluza-Klein theory, the compactified dimensions support standing waves. These standing waves manifest as copies of ordinary particles with additional mass. For each standard model particle, there would be a tower of heavier Kaluza-Klein partners. If the compactified dimensions were relatively large, perhaps 10 to the negative 18 meters rather than 10 to the negative 35 meters, the lightest Kaluza-Klein particles might be light enough for the LHC to produce. These would appear as unexpected resonances, bumps in the distribution of particle masses at specific values. Physicists have searched extensively for such resonances in various channels, pairs of photons, pairs of electrons, pairs of jets, but haven't found any convincing evidence. Another signature would be missing energy. If extra dimensions exist, particles could escape our three-dimensional world by moving into the extra dimensions. In a brane world scenario where standard model particles are confined to a brane but gravity can access the bulk, gravitons could be produced in collisions and escape into extra dimensions. From our perspective on the brane, energy would simply vanish. Particle physics events must conserve momentum and energy. In every collision, the total energy and momentum of all detected particles should balance. But if a graviton carries away energy into extra dimensions, there would be an apparent imbalance, missing energy and momentum that doesn't correspond to any detected particle. Distinguishing this from ordinary missing energy, caused by neutrinos, which interact so weakly they usually escape detection, requires detailed analysis. Physicists look for events with a single jet of particles recoiling against nothing, or events with unusually large amounts of missing transverse momentum. These monojet searches have set stringent limits on extra-dimension models, constraining the size and number of possible extra dimensions. The LHC has also searched for microscopic black holes. Some theories with large extra dimensions predict that the fundamental gravity scale could be much lower than the Planck scale, potentially as low as a few tera-electron volts. At age, these energies, particles in LHC collisions, might come close enough together to form tiny black holes. These microscopic black holes wouldn't be the astrophysical monsters that devour stars. They'd be quantum objects, existing for only about 10 to the negative 26 seconds before evaporating through Hawking radiation, the quantum process by which black holes emit particles and lose mass. The evaporation would produce a distinctive spray of many different particle types with roughly equal energies. Searches for this distinctive signature in LHC data have found nothing. The absence of microscopic black holes rules out many large extra-dimension models and sets lower limits on the fundamental gravity scale. If these models are correct, the extra dimensions must be smaller than initially hoped, or the fundamental gravity scale must be higher. The LHC's negative results might seem disappointing, but they're scientifically valuable. Each experiment that finds nothing still provides information. It rules out part of theoretical parameter space, constraining what's possible. The absence of Kaluza-Klein resonances tells us that if extra dimensions exist, they're smaller than certain sizes. The absence of missing energy signals constrains how large extra dimensions can be if they exist. The absence of black holes tells us the fundamental gravity scale can't be too low. These experiments probe energies and distance scales far beyond anything accessible to previous generations of particle physics experiments. The LHC has pushed the limits by orders of magnitude. If extra dimensions exist at scales not too far below what we can currently reach, the LHC has a chance of seeing them. There are also searches for extra dimensions in gravitational physics. If certain extra dimensions were as large as a millimeter, Newton's gravitational force law would be modified at distances below that scale. Instead of the familiar inverse square law, force proportional to 1 over distance squared, gravity might follow an inverse cube law or higher power at short distances. Experimenters have conducted exquisitely precise measurements of gravitational force at sub-millimeter scales using torsion balances and atomic force microscopes. So far, these experiments confirm Newton's law down to distances of about 50 micrometers, ruling out extra dimensions larger than that scale in certain models. These tests are technically challenging. At such small scales, electrostatic forces, thermal effects, and surface forces can overwhelm gravity, but they provide complementary constraints to collider searches. Astrophysical observations also constrain extra dimensions. If extra dimensions exist, stars and supernovae could lose energy to graviton emission into the bulk. This would affect stellar lifetimes and supernova dynamics. Observations of supernova 1987A, in particular, have been used to constrain some extra dimension scenarios. The supernova's energy, output, and neutrino emission match theoretical predictions, assuming no extra energy loss, limiting the possible properties of extra dimensions. Cosmological observations provide another testing ground. The expansion history of the universe, the formation of cosmic structures, and the properties of the cosmic microwave background radiation all depend on gravitational physics. Extra dimensions would modify gravity on cosmological scales, potentially leaving observable imprints. Current cosmological observations are consistent with standard four-dimensional general relativity, placing constraints on extra-dimension models. Despite decades of experimental effort across multiple frontiers, particle colliders, precision gravity measurements, astrophysics, and cosmology, no definitive evidence for extra dimensions has been found. This doesn't necessarily mean extra dimensions don't exist. It means that if they exist, they're either too small, perhaps Planck-sized as string theory suggests, or too weakly coupled to have produced detectable signals in experiments so far. The experimental limits continue to improve as technology advances and experiments become more sensitive. The LHC is being upgraded to higher luminosity, which will allow it to collect more data and search for rarer processes. Gravitational wave observatories like LIGO might eventually detect signatures of extra dimensions in signals from black hole mergers. Precision measurements continue to push towards smaller scales and lower energies. The search continues. And while we lack direct evidence for extra dimensions, the theoretical reasons for believing they exist remain compelling. Our best theories of fundamental physics strongly suggest that space has more than 3 dimensions. The fact that we haven't seen them yet simply means they are well hidden, as theoretical considerations suggest they should be. This brings us to perhaps the deepest question. Given that the universe apparently has 11 dimensions, why did 3 of them remain large while the others compactified? Why does the observable universe have 3 spatial dimensions specifically? Recent work suggests there might be a profound answer based on thermodynamics and the early universe. The question of why our universe has 3 large spatial dimensions instead of some other number has puzzled physicists for over a century. It's not obvious that 3 is special. Why not 2 dimensions, like a flat sheet? Why not 4, or 5, or 7? This question becomes especially pressing in the context of string theory and M theory. If the universe fundamentally has 10 or 11 dimensions, why did exactly 3 of them remain large while the others compactified? Was it random chance? Was it inevitable? Or is there a deep physical reason that selects 3 dimensions over all other possibilities? Recent theoretical work suggests there might be a profound answer, one that connects to the most fundamental laws of physics, the laws of thermodynamics. According to research by Julian Gonzalez Ayala and colleagues, published in the journal Europhysics Letters in 2016, the emergence of 3 spatial dimensions might have been a thermodynamic necessity, frozen into the structure of space-time during the earliest moments of the universe's history. To understand their proposal, we need to consider what the universe was like in its first fraction of a second after the Big Bang. At these incredibly early times, perhaps 10 to the negative 43 seconds after the beginning, during what's called the Planck epoch, the universe was unimaginably hot and dense. Temperatures exceeded 10 to the 32 degrees Kelvin. Energy densities were enormous. And at these energies, the distinction between different numbers of dimensions might not have been apparent. The universe existed in a kind of symmetric state where all spatial dimensions were on equal footing. As the universe expanded and cooled, however, this symmetry had to break. Dimensions had to choose whether to remain large and expanding or to compactify into tiny, curled-up structures. The question is, what determined which dimensions did what? González Ayala and colleagues proposed that the answer lies in thermodynamics, specifically in a quantity called the Helmholtz free energy density. The Helmholtz free energy, named after the 19th century physicist Hermann von Helmholtz, is a thermodynamic potential that measures how much useful work can be extracted from a system at constant temperature and volume. It combines the internal energy of the system with its entropy, weighted by temperature. For a universe filled with radiation in the early moments after the Big Bang, the Helmholtz free energy density can be calculated as a function of both temperature and the number of spatial dimensions. The researchers showed that this density reaches a maximum value at a specific temperature and a specific dimensionality. That critical dimensionality turned out to be 3 spatial dimensions. Here's the crucial insight. According to the second law of thermodynamics, systems evolve in ways that increase entropy. The second law forbids certain transitions unless sufficient energy is available. When the Helmholtz free energy reaches its maximum value, it becomes thermodynamically forbidden for the system to transition to a different number of dimensions without crossing that maximum. And once the universe cools below the critical temperature, there isn't enough thermal energy available to cross it. In the researchers' calculation, the Helmholtz free energy reached its maximum when the universe had cooled to a certain critical temperature, corresponding to when the universe was just a fraction of a second old. At that moment, space possessed approximately 3 large spatial dimensions. As the universe continued to cool below this critical temperature, the number of spatial dimensions became locked in, frozen by thermodynamics. The system couldn't transition to 4 dimensions or back to 2 dimensions because doing so would violate the second law of thermodynamics at the lower temperatures that followed. Think of it like a phase transition, similar to how water freezes into ice. Above 0 degrees Celsius, water molecules have enough thermal energy to move freely in liquid form. Below 0 degrees, the system freezes into a crystalline structure. The structure is locked in by thermodynamics. Similarly, in this model, the number of spatial dimensions is locked in once the universe cools past the critical temperature. This doesn't mean that the universe necessarily started with an indeterminate number of dimensions. Rather, it suggests that in the very early universe, during the Planck epoch when quantum gravitational effects dominated, dimensional structure might have been fluid or undefined. As the universe cooled and transitioned into a regime where classical spacetime makes sense, thermodynamics selected 3 large spatial dimensions as the stable configuration. This thermodynamics selection principle provides a potential answer to the question, why 3? Not because 3 is mathematically special in some absolute sense, but because 3 is the number that maximizes the Helmholtz free energy density for a radiation-filled universe at the critical temperature that occurred naturally in the cooling process after the Big Bang. However, this is just one proposal, and the field remains active with alternative ideas. Another theoretical framework, developed by Thomas Kephart at Vanderbilt University and colleagues, suggests that 3 dimensions might have been selected through a different mechanism involving flux tubes and knotted structures in the early universe. In their model, during the quark-gluon plasma phase that existed in the first microseconds after the Big Bang, magnetic flux tubes would have formed. These are string-like structures of concentrated magnetic field. If these flux tubes became knotted and linked together like tangled strands of yarn, they could store enormous amounts of energy. When the network of knotted flux tubes collapsed, it would release this energy, potentially driving cosmic inflation. The crucial point in Kiepart's model is that knotted structures are only stable in 3 spatial dimensions. In 4 spatial dimensions or higher, knots can be untied. If you try to tie a knot in a higher dimensional space, it can always be pulled apart without cutting the string. This is a proven theorem in topology, the branch of mathematics that studies the properties of shapes and spaces. Only in 3 dimensions can knots be truly knotted. So in this picture, if the early universe contained flux tubes that formed knots and links, those structures would only be stable if space had exactly 3 large dimensions. If more than 3 dimensions remained large, the flux tubes would untangle, the stored energy would be lost, and inflation might not occur. The requirement for a successful inflationary epoch might have selected 3 dimensions specifically. Both of these proposals, the thermodynamic selection through Helmholtz free energy and the topological selection through flux tube stability, are speculative. They represent attempts to find physical principles that might explain the observed dimensionality of space rather than treating it as an arbitrary input. Neither has been proven or tested experimentally, and it's possible that neither is correct. The true explanation might be something entirely different that we haven't conceived of yet. There's also the anthropic perspective to consider. Perhaps there is no fundamental principle that selected 3 large dimensions. Perhaps the landscape of string theory, with its many possible compactifications, contains universes with all different numbers of large dimensions. Most of those universes might be sterile, unable to support complex structures or life. But in universes with 3 large spatial dimensions, stable atoms can form, stars can burn, planets can orbit, chemistry can develop, and eventually observers can emerge to ask why the universe has the properties it does. From this anthropic viewpoint, we observe 3 spatial dimensions not because 3 is fundamentally special, but because observers can only arise in universes with 3 spatial dimensions. We find ourselves in a 3-dimensional universe for the same reason fish find themselves in water. It's the only environment where creatures like us could exist. This anthropic reasoning is controversial among physicists. Some view it as a cop-out, a way of avoiding the hard work of finding fundamental explanations. Others see it as a legitimate application of Bayesian reasoning. We should condition our theories on the fact that we exist to observe the universe. The debate continues. The question of why 3 dimensions also connects to the deep mystery of why the fundamental constants of nature have the values they do. The mass of the electron, the strength of the electromagnetic force, the value of the cosmological constant, all these numbers appear finely tuned to allow for complex structures and life. Change any of them significantly, and the universe would look radically different. Stars might not form, atoms might not be stable, chemistry might not work. Is this fine-tuning evidence for a multiverse where different regions have different constants and we inhabit a rare, hospitable region? Or is there a deeper theory that predicts these values? The dimensionality of space is another item on this list of apparently fine-tuned properties. We don't yet know whether it's fundamentally explained, anthropically explained, or simply a brute fact about the universe. What we do know is that three spatial dimensions have profound consequences for the physics we observe. They determine how gravity weakens with distance. They affect whether stable orbits are possible. They influence the structure of atoms and the possibility of chemistry. They shape the kinds of complex structures that can form. In a universe with a different number of large spatial dimensions, physics would be unrecognizably different. Computer simulations by Japanese physicists Jun Nishimura, Sang-Woo Kim, and Asato Tsuchiya, published in 2012, attempted to model how dimensional structure might have emerged from the 9 spatial dimensions of string theory. Using a formulation called the EKKT matrix model, they performed calculations simulating the very early universe. Their results suggested that 3 of the 9 spatial dimensions would naturally undergo expansion while the other 6 remained compact. This was the first numerical demonstration that 3-dimensional space could emerge dynamically from a higher dimensional theory. The simulation didn't rely on putting in 3-dimensional space by hand. Instead, 3 dimensions emerged naturally from the dynamics of the theory. This lends support to the idea that 3 dimensions might be selected by fundamental physics rather than being arbitrary. However, we must emphasize that all of these ideas, thermodynamic selection, topological selection, anthropic reasoning, dynamical emergence, remain theoretical. We don't yet have experimental evidence that definitively explains why space has 3 dimensions. We don't have a complete understanding of how dimensional structure emerged in the early universe. These are open questions at the frontier of theoretical physics. What we can say with confidence is that the 3-dimensional nature of space is not arbitrary or meaningless. It's deeply connected to the fundamental structure of the universe, to the properties of matter and forces, to the possibility of complex structures and life. Understanding why we experience 3 dimensions, why 3 and not 2 or 4 or 7, is part of understanding the most basic architecture of reality. As we continue our exploration of hidden dimensions and the structure of space-time, let's turn now to the broader implications of these ideas and the mysteries that remain unsolved. The possibility that our universe contains hidden dimensions beyond the 3 we perceive has profound implications that extend far beyond theoretical physics. If extra dimensions exist, even if they're compactified at the Planck scale or confined to structures we can't directly observe, they fundamentally alter our conception of reality. First, consider what it means for the nature of space itself. We tend to think of space as the emptiness between objects, the stage on which matter and energy perform their interactions. But if extra dimensions exist at every point in space, then space is far richer and more structured than this simple picture suggests. Every point in our 3-dimensional world is actually the intersection of many more dimensions curled up in complex geometric shapes. This means that what we perceive as empty space contains hidden structure. The vacuum isn't truly empty, it's filled with the geometry of the compactified dimensions. This geometry isn't static or inert, it influences the behavior of particles and forces. A particle moving through space is also, in some sense, moving through these extra dimensions, even though its motion in those directions is confined to tiny scales. The properties we observe about particles, their masses, their charges, which forces they respond to, might not be fundamental properties at all. Instead, they might be geometric properties, determined by how strings or fields interact with the shape of the compactified dimensions. An electron might be fundamentally the same thing as a quark, just a string vibrating differently or wrapped around different cycles in the Calabi-Yau manifold. This geometric view of particle physics represents a radical departure from how we've traditionally understood matter. Instead of particles being basic, irreducible entities with properties we simply measure and catalog, particles become manifestations of underlying geometric structures. Physics becomes geometry in a deeper way than even Einstein imagined with general relativity. If this view is correct, then the standard model of particle physics, our incredibly successful description of particles and forces, is an effective theory, a low-energy approximation of a more complete geometric theory operating at the Planck scale. The apparent complexity of the standard model, with its multiple families of particles and numerous parameters, might reflect the complexity of the Calabi-Yau manifold's geometry. This raises the tantalizing possibility that particle physics might someday become more predictive. If we could determine which Calabi-Yau manifold describes our universe, or if we could find principles that select a unique compactification, we might be able to calculate particle masses and force strengths from first principles rather than measuring them experimentally. This would represent a triumph of theoretical physics comparable to Newton's prediction of planetary orbits or Einstein's prediction of gravitational lensing. However, we're very far from this goal. The string theory landscape contains an enormous number of possible vacua, different ways the extra dimensions could be compactified. Estimates suggest there might be 10 to the 500 or more different possibilities. Even if one of these possibilities describes our universe, we currently lack a principle for selecting which one. This is sometimes called the vacuum selection problem, and it's one of the deepest challenges facing string theory. Some physicists argue that this vast landscape is actually a feature, not a bug. If eternal inflation is correct, if the universe underwent a period of exponential expansion in its earliest moments and this inflation continues in other regions beyond our observable patch, then different regions of the multiverse might have different compactifications. Most regions would have physics nothing like ours. Only in rare regions where the compactification produces suitable physics could observers like us arise. This multiverse scenario provides a potential anthropic explanation for why we observe the particular particle physics we do. Other physicists find this unsatisfying. They argue that physics should be predictive, not just explanatory. The multiverse hypothesis, they contend, gives up on the goal of understanding why the universe has its observed properties. If any property can be explained by saying, there's a region of the multiverse where it's different, and we just happen to live in this region, then we've stopped doing science and started doing philosophy. This debate reflects deep disagreement about what counts as a satisfactory scientific explanation. It touches on questions about the nature of physical law, the role of probability in cosmology, and what we should expect from fundamental theories. There's no consensus on these issues, and they remain actively debated. Beyond the vacuum selection problem, string theory and M-theory face other significant challenges. Despite decades of development, we still lack a complete, non-perturbative formulation of M-theory. We understand many of its properties and limits, but we don't have the full theory in the way we have, say, quantum electrodynamics. This incompleteness makes it difficult to extract definitive predictions. Additionally, string theory currently lacks direct experimental evidence. No experiment has detected strings, extra dimensions, or supersymmetric particles. The theory successfully includes gravity at the quantum level and unifies forces mathematically, which are remarkable theoretical achievements. But physics is ultimately an experimental science, and theories must make contact with observation to be fully validated. This doesn't mean string theory is wrong. Many correct theories in physics history initially lacked direct experimental support. General relativity predicted gravitational waves in 1916, but they weren't detected until 2015. Gauge theories in particle physics were developed in the 1950s and 60s, but weren't fully confirmed until the 1970s and 80s. Sometimes, theory leads experiment by decades. The question is, are there testable predictions we might verify in the foreseeable future? Some possibilities exist. Certain compactifications of string theory predict specific patterns in the masses and mixing angles of particles. As experiments like the Large Hadron Collider accumulate more data, these predictions might be tested. String theory also makes statements about quantum gravity that might be testable through precision cosmological observations or tabletop quantum gravity experiments. The theory predicts modifications to black hole thermodynamics, which might be observable in gravitational wave signals from black hole mergers. It makes predictions about cosmic strings, topological defects that might have formed in the early universe and could leave signatures in the cosmic microwave background. Some versions predict specific dark matter candidates that might be detected by underground experiments. None of these tests would constitute a smoking gun, a unique, decisive signature that could only come from string theory. But they could provide evidence that the theory is on the right track, or rule out certain versions of it. As experimental capabilities improve, the window for testing string theory gradually opens. Meanwhile, the mathematical structures that emerge from studying string theory have proven remarkably fruitful in other areas of physics and mathematics. Mirror symmetry, a property of Calabi-Yau manifolds discovered through string theory, has been used to solve long-standing problems in pure mathematics. The ADS-CFT correspondence, which relates string theory in certain spaces to quantum field theories without gravity, has provided new insights into condensed matter physics, nuclear physics, and the quantum properties of black holes. These connections suggest that even if string theory doesn't turn out to be the final theory of fundamental physics, it's revealing deep truths about the mathematical structure of quantum field theory and gravity. The theory has proven to be far too rich and interconnected with established physics to be completely wrong. There are also alternative approaches to quantum gravity that don't require extra dimensions. Loop quantum gravity attempts to quantize space-time itself without introducing strings or higher dimensions. Asymptotic safety proposes that gravity might be quantum mechanically consistent at all scales without requiring extra structure. Causal dynamical triangulations model space-time as a network of simple building blocks. Each of these approaches has its strengths and weaknesses, its proponents and critics. The existence of multiple competing theories of quantum gravity reflects the difficulty of the problem and the lack of experimental guidance. Without data from the Planck scale, theorists must rely on mathematical consistency, elegance, and indirect connections to known physics. Different physicists weigh these criteria differently, leading to different theoretical preferences. What seems clear is that understanding the fundamental structure of space-time, whether it involves extra dimensions, whether it's continuous or discrete, whether it's geometric or emergent, will require new insights and probably new mathematics. We're not yet at the end of this journey. The questions about hidden dimensions, about why we observe three, about how to unify quantum mechanics and gravity, remain open. These questions connect to even deeper mysteries. What is space, really? What is time? Why does the universe exist at all? Why are the laws of physics mathematical? Why is there something rather than nothing? These questions have puzzled philosophers and scientists for millennia, and they remain as mysterious now as ever. The investigation of extra dimensions is part of humanity's long quest to understand the fundamental nature of reality. From ancient Greek philosophers speculating about atoms, to Newton discovering universal laws, to Einstein revealing the geometry of space-time, to quantum physicists uncovering the uncertainty and entanglement at nature's foundations, each generation has pushed deeper, uncovered new layers, revealed new mysteries. Perhaps extra dimensions are part of that deeper structure. Perhaps they'll turn out to be unnecessary, and reality will surprise us in different ways. We don't yet know. What we do know is that the questions are fascinating, the mathematics is beautiful, and the pursuit itself, the human drive to understand, is profound. As we come to the end of our exploration, let's take a moment to reflect on what we've covered and what it means for our understanding of the cosmos and our place within it. For hours now, we've journeyed through some of the most abstract and challenging ideas in modern physics. We've explored dimensions beyond the three we perceive, geometric shapes too complex to visualize, scales too small to observe, and concepts that strain the limits of language and imagination. What emerges from this exploration is a picture of reality that's far stranger and more intricate than everyday experience suggests. The space you occupy right now, the room you're in, the air between these words and your awareness, all of it might contain hidden dimensions, curled up at every point, their geometry determining the fundamental properties of matter and energy. This isn't fantasy or speculation. It's serious science, developed by thousands of researchers over decades, motivated by the mathematics of our most successful physical theories. Whether it's ultimately correct remains to be seen, but the theoretical framework is coherent, mathematically rich, and addresses real problems in fundamental physics. The questions we've explored, why three dimensions, how dimensions can be hidden, what determines particle properties, how to unify forces, are questions about the deepest structure of reality. They're questions that have no impact on your daily life, that won't help you pay bills or fix your car or improve your relationships. Yet they matter in a different way. They speak to something fundamental in human nature, the desire to understand, to know how things really are, to push past surface appearances and glimpse the underlying truth. Throughout history, this desire has driven progress. It led to Newton's laws, which made space travel possible. It led to quantum mechanics, which enabled computers and lasers and modern electronics. It led to general relativity, which is essential for GPS satellites. Basic research into abstract questions has repeatedly yielded practical benefits, often in ways no one anticipated. But even beyond practical applications, understanding matters for its own sake. We're meaning-seeking creatures. We want our lives to make sense, to fit into a coherent picture of how things are. Science provides that picture, continuously refined and expanded as we learn more. The picture of extra dimensions, of a universe with 10 or 11 dimensions, 7 of them compactified into intricate geometric shapes, 3 of them large and hosting the reality we experience, is part of our current best attempt at that comprehensive picture. It might be revised, it might be replaced, but right now it represents the frontier of human understanding about the dimensionality of space. As you return to your three-dimensional world after this exploration, remember that reality might extend in directions you cannot perceive. Every point in space might be richer than it appears. The particles that make up your body might be vibrations of strings in extra dimensions. The forces that hold matter together might be geometric properties of hidden spaces. This hidden complexity doesn't make reality less real. It makes it more wondrous. The universe is deeper than its surface, more intricate than its appearance, more mathematical than its presentation to our senses. And we, through the tools of physics and mathematics, can begin to understand that depth, even if we can't directly perceive it. The exploration continues. Experiments push to higher energies and greater precision. Theorists develop new mathematical tools and new physical insights. Someday, we might have definitive answers about whether extra dimensions exist, what their geometry is, why 3 dimensions are large, or we might discover that the questions themselves need to be reframed, that reality is organized in ways we haven't yet imagined. Either way, the journey is worthwhile. The questions matter. The search for understanding is part of what makes us human. Thank you for spending this time exploring the mystery of dimensions with me. If you've enjoyed this journey into the hidden structures of reality, please consider liking this video and subscribing to Nebula Nights. There are many more cosmic mysteries to explore together, many more questions at the boundaries of human knowledge, many more quiet investigations into the nature of everything. Until next time, rest well, dream deeply, and remember that reality might be far stranger and more beautiful than it appears.